Okay, hi everyone. I'm Trond Andersen from Google Quantum AI. First of all, I want to thank the organizers for this really awesome conference. Thank you so much. Today, I'm going to tell you about our recent development of a high-fidelity hybrid analog-digital quantum simulator. And I want to show you how we use that simulator to study some very interesting thermalization dynamics in the XY model. So let me first motivate this work a little bit by considering recent progress, but also challenges in purely digital NISQ simulation. So first of all, we're now in a very exciting era where we can really start using our quantum hardware to do very interesting things. We can start making discoveries, for instance, of robust bound states of microwave photons, as you see on the left here. We can realize completely new physical phenomena, such as the braiding of non-abelian anyons. We can answer interesting questions, for instance, about the universality class of the dynamics in a Heisenberg spin chain. So clearly, there's a lot of very exciting progress here, but there are also important challenges. A key one is, of course, decoherence, which limits how far into the dynamics we can go in our simulation. And also Trotter errors, which limits our ability to produce really low temperature states. So that motivates the introduction of some analog evolution, which comes with some very nice advantages. A key advantage is that in analog, we have very fast entanglement growth, as is shown on the left here. So here we simulate the entanglement entropy, both in an analog circuit, but also in an analogous digital circuit. You can see it grows much, much faster in the analog case. That's simply because we have all the couplings on at the same time instead of applying layers of gates. Another great advantage is that by directly implementing the Hamiltonian dynamics, we can avoid Trotterization. So we sort of circumvent this eternal issue of a digital simulation where a too small Trotter step gives you decoherence because it's very slow, while a too large one eventually gives you heat death, as is shown for the transverse field Ising model on the right here. Now, of course, analog quantum simulation is not brand new. It has a very rich history, particularly in the cold atoms domain. So a key question here is, what kind of advantages do we have in our Transmon platform that could allow us to do new things here? And there are some key, very nice advantages. The first one here is that we have a very fast repetition rate. So that allows us to do new things in terms of measurements. For instance, we can measure the full counting statistics, as we did when we probed the universality class of the Heisenberg spin dynamics. We also have access to readout in all bases. Combine that with a fast repetition rate, and you can now perform measurements of many-body entanglement in larger subsystems. And I actually want to take this second point here even a bit further, because really what we have here is we have a quite easy access to a hybrid analog-digital operation, where you can sort of get the best of both worlds. You get the very fast evolution of the analog, but then you can also get flexible initial state preparation and extensive final state characterization with the digital part of it. And you'll see a lot of that throughout my presentation today. Okay, so I'm listing all these great advantages of analog and of our Transmon platform. But of course, there's no such thing as a free lunch. And in this case, really the big obstacle is that analog calibration is very challenging in our platform. The explanation for that is quite intuitive. We want to perform some kind of local calibration, as you see here, preferably pairwise, 2 and 2 qubits. We want that in order for this to be scalable. Now, in the digital case, if you perform this calibration, you can almost take it directly to your circuit, because these pairwise calibrations is calibrations of your entangling 2-qubit gates. In analog, that's not the case, because when we go from what we learned on the left to our full-scale experiment on the right, all the dressed or hybridized quantities that we measured completely change. They change because we now turn on all the couplings at the same time. So we get new hybridization in our system. In order to overcome this, we have developed now a new scalable high-fidelity calibration scheme, where the key idea is to explicitly calibrate the bare frequencies, the non-hybridized ones. And the whole reasoning behind that is that the bare frequencies do not change from a local calibration setting to our full-scale experiment. To extract these bare frequencies, we perform a set of carefully chosen 2-qubit spectroscopy measurements that allows us to extract all the information that we need about the system. We then feed that into a very advanced device model that includes all these types of couplings that you can see here. And by modeling this very carefully, we can very accurately extract the bare frequencies. Then finally, we use a projection technique that allows us to get to this spin Hamiltonian that you see here. It's an XY model. You can see that it also has some higher order terms. We can typically keep those about an order of magnitude smaller than the dominant terms. Okay, so that is our new calibration scheme. The first thing we, of course, have to do is we have to benchmark it to see how well it's working. We do that by performing cross-entropy benchmarking. More specifically, we prepare a few of the qubits in the one state. Then we turn on the analog evolution for some time. And then finally, we measure the final distribution of bit strings. We then go and compare that to what we theoretically expect. And that gives us the XEB fidelity, as shown on the right there, as a function of time for various system sizes. What you can see here is that we can go all the way up to 30 cycles. That's about 10 times more than we need to reach maximal entanglement here. So it's a really, really long time. We can do that for 35 qubits, and we still have a very high fidelity in the system. Said differently, our error is only 0.1% per qubit per cycle. It's really quite high. Now, I want to emphasize here that this was achieved through really just careful physics modeling. What's nice about that is that physics modeling is very scalable. So in comparison to some kind of local refitting scheme that would scale poorly with system size, here we have a scheme that works very well, but it's also very scalable. Now, this combination here of this very fast entanglement growth that we have in our system, but also the very high fidelity, makes this very classically challenging. And we estimate that this would take more than 1 million years on Frontier at the full system size of 69 qubits. And just to be clear, a big part of this is that because of the analog dynamics, we very quickly get to this maximally entangled state with very little effects of decoherence. Another way to consider this combination of this very fast entanglement growth and the high fidelity is to consider what's called the mixed state entanglement proxy. That's a very intuitive measure. It's really just the effective entanglement after we account for loss of fidelity. That's what's plotted on the right here as a function of system size for a few different platforms. And you can immediately see that our new platform in the top right corner here performs very well. It allows us to get a lot of entanglement with very little fidelity loss. You can in particular see it's very close to this ideal line. Of course, this makes us very excited for the kind of physics that we can explore with this new platform. And that brings me to the second part of the talk, where I will show you our first physics study with this new platform that we have. So here we're going to explore the rich phase diagram of the XY model. We're going to do that by first turning on a very simple staggered field, Z field Hamiltonian. We'll prepare our system in the ground state of that simple Hamiltonian, so just an antiferromagnet. And then we're going to ramp to the XY model. And by varying the ramp rate, we hope to explore different parts of the phase diagram. In particular, there are two particular things that we want to look for here. One of them is a Kosterlitz-Thouless transition. So we're hoping that we can get to a sufficiently low temperature where free vortices become entropically unfavorable. We would like to see if we can see some transition from exponential decay of correlations to a power law decay. In addition to that, we expect that as we're ramping, there should come a point where the system is no longer able to respond to the changes in Hamiltonian, when the gap becomes smaller than the inverse of the remaining time. And at this point, we expect that the system should sort of freeze with a correlation length that's a power law in the ramp time. That's what's known as the Kibble-Zurich mechanism, and we want to study that as well. Okay, so let's start out sort of simple. Let's first just measure the energy, the final energy in our system. That's XX plus YY, nearest neighbor correlators, as a function of time. I show you that here both for experiment in red and also simulation in blue. You can immediately see that we are able to get very close to the ground state. We actually get 95% of the way there. The ground state is shown here in the gray line. You can also notice that we actually managed to get past the expected critical temperature for the Kosterlitz-Thouless transition as well. I want to emphasize one thing here, which is I have two experimental measurements. The second one, you can see, gets lower. That's a measurement where we leverage our digital analog capabilities, and we perform an entangling gate right before the measurement. That allows us to measure in the Bell basis and post-select our energy measurements. I'm not going to get into too much detail about it, but if you have any questions about it, please feel free to ask after the talk. But at least this is showing already some of the advantages that we get from this digital analog hybridization here. Okay, so that was the energy. That was nearest neighbor correlators. Let's take this a step further and now look at longer range correlations. So that's what I show you here. Here I plot the average correlation between pairs of qubits that are separated by some vector r. As we go from the top left to the bottom right, we're extending the ramp. You can see that we really get longer and longer ranged correlations, and at the longest ramp times, actually, these correlations, they really extend across the entire sample. And I want to emphasize that this is not a state that we would be able to produce with a purely digital protocol. Now what we can do is we can now perform an average so that we can convert this to what we have on the right here, which is the correlations as a function of radial distance. So we're just averaging around circles. Here we already start seeing something interesting. We now see that at very short ramp times, the correlations decay sort of exponentially with distance. But at longer ones, they start looking more power law-like. To convince you further about that, let's consider now a few different signatures of the Kosterlitz-Thouless transition. Let's start with the easiest one. We want the energy to be below an expected transition energy. Indeed, I showed you that we were able to do that. Next, I mentioned that we're interested in what the decay of these correlations look like. Is it exponential? Is it power law? So let's plot the ratio of the error that we make in a power law fit versus the error that we make in an exponential fit. You can see that that ratio is initially above 1, so exponential fits are best. But then suddenly we have this pretty sharp drop exactly when we go below the transition temperature, and suddenly we see that the power law starts agreeing better, consistent with what we expect at the Kosterlitz-Thouless transition. There's also this very nice prediction that there should be a universal decay exponent at the transition of 1/4. And indeed, in the same regime, we find that we get extremely close to 1/4. We're at 0.28 or something like that. Finally, with our hybrid capabilities, we can very easily go and measure the correlators that we need in order to reconstruct the vortex density in our system. And we also find that the number of vortices in the systems also drops, let's see, very sharply in the same regime. So all of these are kind of consistent signatures of a Kosterlitz-Thouless transition. I also mentioned that we're interested in how the correlation length depends on the ramp time. So that's what's plotted on the left here. Again, I plot both experiment and simulation, but now I've also included the prediction from Kibble-Zurich theory. You can immediately see here that these curves don't agree well at all. Initially, this was kind of concerning to us. We were very confused about it. Then to try to understand it better, we decided, let's try to measure the correlation length, not just at the end of the ramp, but also throughout the ramp that we're performing. So that's what I show you on the right here for a few different ramp rates. And I've also here included the point where we expect that the system should freeze. Again, this is the point where the gap becomes smaller than the inverse of the time that's left. What you can immediately see is that the system absolutely does not freeze. The correlation length keeps increasing a lot, actually. And so what we're seeing here is the coarsening of the correlated domains, which really breaks down the Kibble-Zurich mechanism. Now, as sort of a sanity check, we can pretend that this coarsening didn't happen and kind of just stop the measurement right here, so we can go and measure there instead. We can then put that back in the left plot, and now actually we find that it does agree with the Kibble-Zurich mechanism, so this sort of perfectly makes sense. Okay, so far we've been tuning our final state by using the ramp rate. That's worked nicely, but there are still some limitations. And one other way that we can tune this is we can instead inject excitations at the very beginning of the experiment. So I said that we start out with this antiferromagnetic state. We can go and flip some of the spins in that state in order to inject energy. That's what we've done on the left here. So here on the x-axis, I'm varying how many excitations do I inject at the beginning. I then find that the energy increases. That makes sense. I'm injecting more energy. I get a higher energy. I also find that the correlation length decreases. But to really get some nice insights out of this data on the left here, what we can do is we can take all of that data and we can plot it on the same axes. That's what I've done on the right here. So here is all the data where I'm varying both ramp rate and also excitation number. And on the axis, I put the correlation length and a function of the energy. And what we find here is that all this data collapses onto one curve. And this makes perfect sense because we know from the eigenstate thermalization hypothesis that even though I was preparing these states in different ways, if I ever end up with the same energy and this state thermalizes, I should also end up with the same observable. And indeed, I end up with the same correlation length in the main plot, and I end up with the same vortex density in the inset. Okay, so far we've tuned our states now both with the ramp rate and also with initial excitations. These are very powerful knobs, but they come with one common big limitation, which is that if I want a substantial amount of correlations, I need to ramp for quite a while. At the end of that long ramp, most of the thermalization dynamics, which are very fast, are already done. And so as a consequence of that, I've been showing you all these examples of thermalization, but I never actually showed you the thermalization dynamics themselves, because at the end of the ramp, they were pretty much done. Another limitation is that that only allowed us to tune the energy of our system. We couldn't really access other observables. That motivates the very last part of my presentation, where we're now going to fully take advantage of this hybrid digital-analog operation. And we're going to use digital gates to prepare pairwise entangled states that allows us to immediately inject correlations into the system so that we can, from the very start, go and watch the thermalization dynamics real time. In addition to that, as I'll show you, this will also allow us to tune not just the energy, but now also vorticity, spin current, and also the spatial profile of these observables. So more specifically, what we're going to do is we're going to prepare these kind of dimers that you see here. They are tuned by this phase phi. That gives us a lot of power that allows us to tune both the energy. We can tune to negative or positive energies at 0 and pi. And we can also tune the spin current if we use a phase of pi over 2. So we now have full control of the initial state. Let's start out with the simplest case, where we just prepare all the dimers in the same state. They're all very low energy dimers. Here, what we can now finally watch real time is the thermalization dynamics. They're extremely fast, just 1.5 cycles to get to a almost perfectly thermalized state. And during this, we can also now watch the correlations. We can really see the correlation lengths increasing. We can now watch the coarsening real time after we initialized our system. And in particular, the coarsening here extends the correlation length to the value that's predicted by ETH. So again, it matches with our other preparation techniques as well. But we don't need to stop there. We can now prepare 2 different types of dimers. So we can prepare some low energy ones on the right side, some high energy ones on the left side. And now we can take it much further. Now we can really watch energy transport from one side to the other. Notice how the time scale is now much, much longer. It's more than an order of magnitude longer to really finish the dynamics here. So here, by using these dimers, we're really allowing ourselves to discover different types of dynamics in our system. On the right here, I've included the energy at vertical cuts as a function of time. That's just to show you that this fits perfectly with a very simple diffusion model. It's almost hard to see the model, but that's the line right behind the data here. So it really agrees perfectly with diffusive transport. Finally, we're going to take this another step further, and now not just prepare phases of 0 and pi, but now dimers with a pi half phase. That's now a spin current. So now we're not just tuning the energy, now we're actually injecting some current from the very start. So here we're watching now the thermalization of the current, or if you want, the vorticity. That's just the current around the plaquettes. And we're now back to very fast dynamics. So here the thermalization takes about just 1 analog cycle. That brings me to the summary of the talk. I've shown you that we've developed this new calibration scheme that allows us to have analog evolution with a very high fidelity, just 0.1% error per qubit per cycle. We then combined that with digital gates that allowed us to have a very flexible initial state preparation. We had great control over the final energy of the state, and it also gave us this very extensive final state characterization as well. This allowed us then to both study signatures of the Kostelis-Thouless transition. We also saw some nice signs of ETH, and then we observed this interesting breakdown of the Kibble-Zurich mechanism. So to end this, I just want to say that we're very excited about this new platform that we have at hand here, and we're very excited to start using this for beyond classical study of various quantum many-body phenomena. So with that, thank you so much, and I'll be happy to take questions.
Thank you for the nice talk, Trond. So questions up there.
Yeah, thanks for the nice results. I'm wondering, so can you really expect power law correlations for the system you showed for the small system sizes? I mean, usually those just emerge in really much bigger systems. So I was wondering about that. And maybe a second question also, be interesting, can you quantify the heating rates? So if you just, for example, hold the system, you create your lowest energy density state, you just hold it there, you know, what's the heating rate as a function of coupling times that you have when you have all the couplings on, just to get a feeling how this compares to other platforms?
Yes. Yes, let's start with the first one. Definitely, we're very much aware that in the best case, we should study this in an even larger system. I completely agree. I think this probably affects our power law decay a bit. I mean, this ratio that you saw, it doesn't get perfect. It probably could get even better in a larger system. That's something that we're very much aware of. We decided to try and see if it's still possible to see some of these signatures. I would definitely say it looks, I mean, a lot of this looks very much like what we're looking for. But I agree, and yeah, we've tried to be careful about pointing out that there are certainly effects like that as well. With the heating rate, I could give you a number in sort of the, let me think. So I know from some of our measurements, let me think, so that's, I can leave it there for 200 nanoseconds, which is about 12 analog cycles. And in that case, my energy changes from 0.25 J to 0.23 J, which I guess should be sort of a universal enough units that that's something meaningful. But that's, yeah, that's the best value I would be able to give you. But that's, I mean, I guess, most importantly, that's a pretty long time where you're still very close to the same energy that you left it at. I would also imagine that it probably depends quite a bit on which energy we leave it at. The value I gave you now is when we prepare it halfway to the ground state. That's what we get when we do this dimer preparation. I would expect that the heating is probably a bit faster than that when we're at the ground state, or very close to the ground state. And that's kind of what you see, you start seeing here. So when we go from 20 cycles and up to 60, you can start seeing that we're sort of heating away from the state as well. Of course, this is not leaving it there. It's during the ramp, I know, but it should still be relatively simple.
Very nice talk, Trond. So following up on Emmanuel's question, people had similar problem with cold atoms, distinguishing power law correlations from exponential. Mm-hmm. And what was useful is to look not at two-point correlation functions, but to look at full distribution function of, say, like X component of the order parameter over a certain length.
Okay.
And it turned out that in that case, you can see a crossover from like exponential distribution function to Gumbel distribution function, which was kind of easier to discriminate.
I see.
Regimes. So.
Yeah, no, so we tried a few different things. We also tried plotting sort of an exponential times power law and these distributions as well. But yeah, no, certainly we should test that. Yeah.
But I also have a question. So it's nice that you have XY model. Can you also turn it into the Sine-Gordon model, for which obviously theorists have done quite a bit?
Sorry, to which model?
Sine-Gordon model. So it's like your XY model plus magnetic field along the X direction.
Yes, we can. So we don't do that yet. You would have to turn on microwaves to do it. I don't see immediately a very big reason why it shouldn't work. And we have actually started doing some things where we do that. So that should be possible.
Because that's an example of exactly solvable model, and there are many beautiful theoretical results, which would be nice to test.
Yeah, no, absolutely. And I should say we're really very much thinking about how we can extend this to other Hamiltonians. And I'm actually happy to see, I think we have quite a lot of freedom actually in adding microwaves, but also doing certain other things to get ourselves to not just the XY model, but other variations as well.
All right, we're already into the break, so we'll stop there. But let's thank Trond again.